Hey guys, it's finally time for us to learn how to solve linear equations, specifically linear equations in one variable for the time being. In this lesson, we will be focusing on the balancing method. But before that, a couple of things to note.
Note 1.
Firstly, what does it mean to solve a linear equation or to solve any equation for that matter? In simple terms, the solution of an equation is the value of the variable which satisfies the equality. For instance, if I say x plus 1 equals to 2, we need to find the solution of the equation or solve for x in this equation. Therefore, we need to find out what value of x when added to 1 would give us 2. That is to say, would make this equation hold true. Now, if we think mentally and intuitively without any technique, then x plus 1 equals to 2. So x must be 1 because only 1 plus 1 can give us 2. Therefore, we would say that the solution of this equation is x equals to 1.
Note 2.
Secondly, whilst we have touched on this in previous lessons, I want to make explicitly clear left hand side and right hand side. You already know that an equation sets two expressions as equal, so there is something to the left of the equal to sign as well as something to the right of the equal to sign in an equation. What is to the left is called as the left hand side, and what is to the right is called as the right hand side. Now, left hand side or right hand side, nobody has the time to say such things all the time. So we frequently use the abbreviations of LHS and RHS in mathematics. Now, to be very clear, saying 1 plus 1 equals to 2 or saying 2 equals to 1 plus 1, that is to say reversing the equation, that's all right and they're both fine and one and the same. But you need to arbitrarily pick one so that you know what's on the left, what's on the right, and which one is to be referred to as which. LHS and RHS are two terms that I expect you to increasingly grow comfortable to.
Before you carry on with your silly little math, I want to tell a story. Hear me out. Once upon a time, in a land far away, there lived a pair of twins. Mischievous little Jimmy and responsible old Timmy were identical twins. Once, as the duo was returning from school, they noticed something. The local playground had a new ride. It was a seesaw. The twins rushed towards it, putting aside their school bags and jumping onto each end. For those of you who haven't ridden a seesaw, let me explain what it is. The seesaw is a ride wherein two people sit on opposite seats, which go up and down, depending on how much weight is on each end of the seesaw. The heavier seat goes down, while the lighter one rises. Jimmy sat on the left and Timmy on the right of the seesaw, and their identical weights balanced the seesaw at first. But Jimmy was in the mood for fun, and wanted to upset the balance of the seesaw. Picking up and wearing his school bag, he grinned, as adding the weight of a school bag to the left end of the seesaw made his end heavier. But Timmy was quick, he wore his own school bag, thus adding an equal weight to the right end, and restoring the balance. Jimmy tried to outsmart his brother by taking off his shoes, thereby subtracting the weight of his shoes from the left end, and disturbing the seesaw balance. But Timmy realized what was happening. He removed his own shoes as well, thus reducing an equal weight from the right end, and exclaimed triumphantly as the seesaw balance was re-established. Whatever Jimmy did on one side, Timmy would copy on the other, never letting the seesaw stay imbalanced for more than a second. And with that, the tale of the twins ends.
Now, if you're done listening to stories, let's get back to some mathematics, shall we? Now, when I gave you the question x plus 1 equals to 2, we were able to solve it But oftentimes, the equation is not so straightforward. The value that the variable might be hiding is not immediately clear. When that is the case and the answer doesn't jump out to us straight away, as it often does not, we need methods and techniques. In this lesson, as I said, we're going to look at the balancing method. Simply put, what does the balancing method state? Do the same operation on both sides of the equation in such a way that the variable is isolated on one side of the equation and all of the constants are on the other side. So what does it mean? First of all, we want to find out from a really complicated little equation what the value of x is. That is to say, we want to know x equals to what? X equals to something. So we need x on one side of the equation and all of the other numbers on the other side. So that explains the need for isolating the variable. But what does it mean to do the same operation on both sides of the equation? Let me state this based on our current knowledge of the 4 arithmetic operations as 4 rules, and let's see if it becomes clear to you why we can do this. You can add the same number to both sides of an equation. You can subtract the same number from both sides of the equation. You can multiply the same non-zero number to both sides of the equation. You can divide the same non-zero number to both sides of the equation. If an equation is just a balance of two things, then if you do the same action on both of those things simultaneously, then can it be the case that we are retaining that balance? We're making some changes, but those changes are being made to an equal extent to both sides of the equation. Just like Timmy was doing to Jimmy when they were riding on the seesaw. Let us understand this through a series of examples.
Example 1.
3x plus 8 equals to 20. Now, you will try to solve this by guessing the value of x, but maybe you might get at the final answer, but it will take you quite some time. Let's do this with a more systematic approach, the approach that incorporates the balancing method. We need to isolate x on one side. So on the LHS, we've got 3x plus 8. So we've got 3 being multiplied to x and we've got a plus 8 as well. So let's try to eliminate all of these things one by one. Let's subtract 8 from both sides of the equation because we don't want that plus 8 on the LHS because we want x to stay alone. So we need to do it on both sides. So 3x plus 8 minus 8, 3x. LHS is now 3x. And the RHS, which was originally 20, becomes 20 minus 8, so 12. So after subtracting 8 from both sides, we have changed 3x plus 8 equals to 20 to 3x equals to 12. So the equation looks different, but at the core of it, it is still the same. But x is not alone just yet. We still have the 3 being multiplied to x. So what do? We divide both sides by 3. So LHS would become 3x upon 3 equals to just x. RHS would become 12 upon 3 equals to 4. So now we have reduced our equation to x equals to 4. Do we need to do anything else? No, because we've arrived at the answer that we were looking for. X equals to what? X equals to 4. Now, let's verify this. Our original equation was 3x plus 8 equals to 20. We said x equals to 4. Let's substitute 4 in place of x in the original equation and see if it actually works. So x, put 4 there, so you would have on the LHS 3 into 4 plus 8. That is 12 plus 8. That is 20. And RHS is 20 as well. Therefore, x equals to 4 is the solution to this equation.
Example 2.
Y upon 2 minus 1 equals to 5. So again, we've got y upon 2 minus 1. A lot of unnecessary stuff on the same side as the variable. We want to cut down on all of that. So let's first add 1 to both sides of the equation so that we can get rid of the minus 1, because minus 1 plus 1 would cancel out. So we would add 1 to both sides of the equation. The LHS would become y upon 2 minus 1 plus 1 equals to y upon 2. The RHS would become 5 plus 1 equals to 6. So we have now changed our equation to y upon 2 equals to 6. How do we get rid of the 2 in the denominator in the LHS? We multiply both sides of the equation with 2. So multiplying the LHS with 2 would give us y upon 2 whole multiplied by 2. That is nothing but y itself. The RHS would become 6 multiplied by 2 equals to 12. Therefore, our final equation and the answer is y equals to 12. Again, let's verify this just to be absolutely 100% certain. Our original equation was y upon 2 minus 1 equals to 5. So put y equals to 12. We would have 12 upon 2 minus 1 equals to 5. 12 upon 2 minus 1 is nothing but 6 minus 1, which is nothing but 5. And thus 5 equals to 5. So indeed, the solution of this equation is y equals to 12.
Example 3.
3x upon 4 equals to 5. Now there is something in the numerator as well as in the denominator on the left hand side which is superfluous. The 3 and the 4 both are good riddance for us. So what do? Let's multiply both sides by 4 so that we can cancel out that 4 in the denominator. So we have the LHS becoming 3x upon 4 whole multiplied by 4. So 4 in the numerator and 4 in the denominator nullify each other. And in the RHS, we have 5 into 4, so that becomes 20. So our equation is now 3x equals to 20. What do we do next? We divide both sides of the equation by 3. So the LHS would become 3x upon 3. That is just x. We're getting quite close now. And to the RHS, it would become 20 upon 3. And we can't simplify 20 upon 3 unless you want to write it in decimal format, which is your choice. But finally, our answer is x equals to 20 upon 3. Now, you would never tell me that 20 upon 3 is a value that you would have run through if you were to solve this equation by guesswork or by trial and error. So the solution to the equation 3x upon 4 equals to 5 by our nice little balancing method is x equals to 20 upon 3. I hope you're now comfortable with solving linear equations in one variable through the Jimmy Timmy game or the balancing method. Whilst I would have loved to give you questions on this for practice, I don't think the balancing method is what you should be taking away. There is a quicker and more efficient method that I hope to teach you in the next lesson, through which you can solve linear equations in one variable with greater ease. So we'll be doing more questions then. But before concluding this lesson, I think a couple of clarifications ought to be in order. Firstly, you may recall me using the phrase non-zero number when stating the rules of multiplication and division on both sides of the equation under balancing method. Why did I say that you can only multiply or divide both sides of the equation by a non-zero number? That is to say, any number, positive, negative, fractional, decimal, any number except 0. For multiplication, because if you multiplied both sides of the equation with 0, anything multiplied by 0 gives you 0. So you would end up with the LHS becoming 0, the RHS becoming 0, and thus 0 equals to 0, which is technically correct, but meaningless and unhelpful, I guess. So don't multiply by 0. And similarly, division by 0, anything, whether an expression or even a number, you as a rule of mathematics can never divide anything by 0. I might explain this at a later date, or you can look this up on the internet, but take it as a rule for the time being. Secondly, there are different ways of applying the balancing method. Even for the examples that we just ran through, you could have used that same concept of balancing in a different way. Let me give you a quick example for hint. 3x plus 8 equals to 20. I encourage you to divide both sides by 3 and then subtract 8 upon 3 from both sides of the equation and see what happens then. You need to be a bit comfortable with fractions for doing this, but if you are, then try it out and see which approach you like better. But if you don't, never mind. What we learned through the examples is ample. Alright then, let's end this lesson for now. Balancing method is fun, but watch out for the next lesson because it contains something even more powerful. Comment your doubts below, subscribe for more, share this with your friends. Catch you in the next one.